So continuing on with this idea of lines, there are times when the slopes aren't terribly nice. So we dealt with slopes that were either positive or negative in the last video. Sorry, I had to do something for a second. But let's try and find the slope between these 2 points. Now you'll notice something. There's the same x-coordinate. Okay, well, let's try it anyway. I'm just going to choose this as x2. Even though the x-coordinates are the same, I'm just going to choose this one as x2, because why not? Y2, and then this is x1, and this is y1. So let's try it. So y2 minus y1. That's 5 minus 4. Great. Over 3 minus 3. And if we simplify this, we'll notice we'll get this. Now, this is a problem. We can't divide by 0. You'll explore this later in later math classes, why we can't divide by 0 and why it doesn't work. But it's just an impossibility. So what this looks like on a graph is the slope is just straight up vertical. And what we do is, since 3 is just our x-coordinate, we'll just, this is 3. Our line is literally just going to look like this. Okay, you know what? It has to go through x-coordinate 3. Our line is literally just going to look like this. It's going to be a vertical line that just goes straight through x equals 3. And the equation for that is literally what I said. Now there's another case where we might have something like this. Okay. X is bigger here, so I'm just going to choose this as x2. Let's see, y2 minus y1. 3 minus 3. Oh, okay. 4 minus 2. Well, we get 0 over 2. It doesn't matter what the denominator is. If we have 0 on the top, the whole thing's just 0. So 0 slope, what does that mean? That means that our y-coordinate is not changing as x changes. Right? Or if you just plot the points, you'll just see this. The only line that connects these 2 points is a flat line. So a slope of 0 just means a horizontal line. And the equation for this is y equals 3. So to summarize, pretty much, if you have a horizontal line, it's just going to be y equals whatever this number is. And if you have a vertical line, it's just going to be x equals whatever the x-coordinate is. So now we get to a bit more of an analytical part using lines. And that has to do with lines that are parallel and lines that are perpendicular. To review, lines that are parallel are lines that never touch. So lines like this. Like you've seen them all the time in real life. And perpendicular lines are kind of the opposite of that. Two perpendicular lines like this. And they intersect at right angles. Now, what does this mean mathematically? Perpendicular lines are lines with the same slope. So, for example, My gosh. Let's just graph both of these for a sec. Y equals 2x, okay. So, y-intercept for this guy is 0. And, okay, up 2 over 1. Okay, great. Lines like that. That's how you graph y equals 2x. Now, y-intercept for this guy, comma 1, right? We're going to go up 2 over 1. If lines have the same slope and a different y-intercept, they're never going to touch. They're just going to keep going and extending on for infinity, but they're just not going to touch. They will never intersect each other. Now, perpendicular lines, if you think about it, what they do is they flip direction, or they swap their slopes, and then they'll reverse the direction, kind of. And let me give an example of that. So we already graphed y equals 2x. Just going to regraph it again. It's going to be something like that. It's actually pretty nice. Wow, surprising. We know y-intercept for this guy is going to be this. And actually what we're going to do is we're going to go down 1 and over 2. Because we're going down 1, and then we're going to go over 2 in the x direction. That's how you graph using a slope like that. So our line, this guy, is going to look like this, kind of. And actually, that sucks. That's terrible drawing. Let me try and get a better one. Actually, you know what? All right. I'm going to use a better example. An example that won't suck as much. X equals 1, we already know. It's going to look like this. Y equals 2. Boom. That's an example of what perpendicular lines look like. So, an interesting fact about perpendicular lines is that they're going to have the negative slope of the line they're perpendicular to. So, let's say the line that is perpendicular to the line y equals 2x is going to have a slope of negative 1/2. So, what you do is you just take the reciprocal of 2, and then you divide by that, and then you multiply it by negative 1. The reason why it didn't work in my previous example is because, well, I mean, it did work. It's just my drawing sucks, and I don't have good scaling. So, whatever. But that's the rule for perpendicular and parallel lines. So, let's do... Let's do an example of the two. Oh man, I have to find an example. Wow. All right, let's use an example from previous video. So, why don't we do this? Finds Alright, I just made that up on the spot. But, yeah. So, what we discussed before, to do letter A, the line that's parallel will have the slope of 2. That's already important. And now, we just put it into point slope form. Yeah, point slope form. So, we just take this point, and we do it in point slope form, which is just y minus 5 is equal to 2 times x minus 2. And we just simplify. So what is that? Y equals 2x plus 1. This is the line parallel to the line y equals 2x plus 2 and passing through the point 2, 5. Now, we'll do the same thing for B. Well, not the same thing, but similar. Perpendicular means negative reciprocal slope, pretty much. So we're going to take this slope, I'm going to take the reciprocal of it, which is 1/2, multiply it times -1. That's our slope. Now we just use point slope form again. So y minus 0 is just 0. And then just multiply. Be careful of your negatives, and you should be chilling. And this is the point. This is the line that is perpendicular to the line y equals 2x plus 2, and passes through the point 1, 0. Now I want to introduce one more thing, and while this is pretty important when it comes to lines, and this is the idea of systems of equations. So previously, we've been solving for equations of one variable, and you couldn't really find equations that had two variables in them. We can now kind of do this when we have systems of equations. And I'll introduce them in more depth in the next video. So a system of equations would be, why does it do that? Bruh. Okay. Something like this. And the question that is being asked here is, what points makes both equations true? Well, the idea of what point makes both equations true, if you think about it graphically, it's where both of the lines intersect. So I'm not actually going to graph these correctly, but okay, it'll look something like this. The point at which, the x, y point, where both the equations are true is where they intersect, because that's where they're equal to each other. And that's how we solve these systems of equations. Now, there's many different ways that you can actually solve them. The first thing I would probably look at is, both these are equal to y, so I can just set them equal to each other. I can say x plus 2 is equal to negative x plus 4. Okay, then I can solve for the x coordinate that makes this true. Add x over and move the 2 over here probably. So 2x is equal to 2, x is equal to 1. That's the x coordinate which they intersect, right? And now I can plug it into one of these equations. So y equals, x equals 1, so we just plug 1 in for x. Y equals 3. So the point at which these two equations are satisfied is this. That's the idea behind systems of equations, but you might be noticing there are 2, or actually 3, situations that can occur with lines when it comes to these equations. So what if 2 systems are parallel? Actually, you know what? I'm just going to get through all the system of equations stuff now. Scratch what I said about doing it in the next video. I'm just going to do it now. But what if 2 lines are parallel? Well, if we do the same thing I just did, set them equal to each other, well, if I subtract 2x from both sides, we get a bit of an issue. Guys, does 2 equal 4? You know it might. Yeah. Nah, JK. But this is a false statement. If you end up solving for something and you end up getting a false statement, that means there's no solution. There's no xy coordinate that will make this true at all. And we can see this on a graph. If we were to graph both of these lines, 2x plus 2 and 4, it looks something like this, right? I said that the solution to a system of equations is where lines will intersect. But these lines are never going to intersect. They're never going to equal each other. And so it makes sense why there's no solution. But there is a case where there's infinite solutions. Now, how does that even happen? Well, let me get a practice problem really quickly. So let's say we have something like this. So y equals 2x plus 1 well, we can solve for y for this guy. And if you do that, you'll see this. That's strange. It's the same line, right? Well, let's set them equal to each other, see what happens. Oops. One sec. Let's get rid of the x. If I get some sort of true statement, 1 is equal to 1, this is true, always, then that means that there's infinite solutions. And what this means graphically is that the two equations that I just put up here are the same exact line. So you can think about it like this. You can think about it like the lines just being layered on top of each other. And so they intersect at every single point. So there's infinite x coordinates and infinite y coordinates where they intersect. that's the basic idea behind systems of equations, or at least single variable systems of equations. And you'll be given questions that will say where these lines intersect and stuff like that. But yeah.